Oxidation-reduction reactions. These are reactions that involve the transfer of electrons. The long name is oxidation reduction. The short name is redox, which always looks like red box to me. But is redox. Red or read for reduction, ox for oxidation. I guess ox-red sounded dumb, so they switched the order. So redox reactions are very common. You use them in your everyday life. Anybody using a battery today of any sort? Do you have a cell phone? You have redox reactions occurring inside your cell phone in your pocket. The production of electricity in a battery involves oxidation-reduction reactions. If you bleach your hair, that is an oxidation-reduction reaction. Rusting of iron, that's not usually a desirable thing, but it happens whether we like it or not. That's also a redox reaction. What we'll see is that many, but not all, of these sorts of reactions involve oxygen. Here are some examples. This is the reaction that powers the space shuttle. It's the combination of hydrogen and oxygen gases to form water. Generates a lot of energy and can propel the space shuttle. Here is an equation describing the rusting of iron. We have solid iron reacting with oxygen to form iron 3 sulfide, which is rust. Very different in its physical properties than the original iron. And here we have the combustion of natural gas. You turn on a Bunsen burner in the lab, or you turn on the gas burner on your stove at home. This is the reaction that is occurring. So these oxidation-reduction reactions are all over the place. There are also some that do not involve oxygen. Here's an example. The reaction of sodium metal with chlorine gas produces sodium chloride. This is an oxidation-reduction reaction, but there's no oxygen present. If we look at the fundamental definition of oxidation as being the loss of electrons, and the definition of reduction as being the gain of electrons, we can see why this reaction is an oxidation-reduction reaction. What are the two ions that are present in sodium chloride? How about sodium and chloride, right? Yeah, it wasn't supposed to be hard. Sodium ion and chloride ion. How is this sodium atom different from this sodium ion? Has to do with the electrons. To become positive, it must have lost an electron, right? So sodium lost an electron. Loss of electrons is oxidation. The sodium was oxidized. Here, chlorine, it's a molecule of 2 chlorine atoms with no charge. Over here, chlorine is an ion with a negative charge. It became an ion by accepting or gaining an electron. So the chlorine was reduced. Reduction is the gain of electrons. Okay, so this is an oxidation-reduction reaction. This is a mnemonic that's helpful to remember these definitions. Bless you. Oil rig. So oxidation is loss of electrons. Reduction is gain of electrons. We have to have oxidation and reduction occurring together. If one substance loses electrons, another substance has to gain them. Okay, you can't just have electrons appearing or disappearing, and the electrons are not going to just go off by themselves either. Okay, it's a little bit like transferring money between your checking account and your saving account. If you take money out of one, it goes into the other. If you take it out of the other one, it goes into the first one. It doesn't just disappear, it's transferring back and forth. If someone loses an electron, then somebody else has to gain the electron. So for now, what you need to be able to do is just identify by looking at an equation if it's an oxidation-reduction reaction. And so here are the guidelines. If you see a substance reacting with elemental oxygen, so that means that you've got O2 as one of your reactants. It's going to be an oxidation-reduction reaction. If you see a metal reacting with a nonmetal, a metal element with a nonmetal element, and so that's sodium plus chlorine, a metal element, a nonmetal element. That's an oxidation-reduction reaction. The more general definition is one substance transferring electrons to another substance. This is not always obvious. So these first two guidelines are good. So let's identify redox reactions. So this first one, 2 lithium plus chlorine forming 2 lithium chloride. Is that a redox reaction? Yes. How do we know? We've got a metal element reacting with a nonmetal element. How about this one? We've got aluminum plus tin ion forming aluminum ion plus tin, the element. What's happening when aluminum goes from an atom to an ion? Does that involve electrons? Yeah. So what's happening here is that the aluminum is losing electrons to become a positively charged ion. It's giving those electrons to the tin. The tin is gaining electrons and becoming a neutral atom again. So that is also a redox reaction. How about letter C? Lead nitrate and lithium chloride to form lead chloride and lithium nitrate. Is it a metal reacting with a nonmetal? No. Is it a metal is it something reacting with elemental oxygen? No. So just based on those two things, we might say no. But based on those two things, we might have said no to this as well. Well, let's think about this. What's happening in this reaction? Here we've got lead and nitrate, lithium and chloride, and over here they've swapped partners. Now the lead is with the chloride and the lithium is with the nitrate. In the reactions that we've done, the charges on these ions don't change. They're just swapping partners. There's no transfer of electrons, they're just switching partners. So this is not a redox reaction. How about letter D? Yes, we've got elemental oxygen here, O2. If O2 is one of the reactants, it's a redox reaction. Any questions? This is identifying these is a little bit tricky at this level because there's a bunch of other stuff that we're not telling you. And so I'll try very hard not to trick you on an exam. Can't promise, but I will try. Combustion reactions. A combustion reaction is a subcategory of redox reactions. All combustion reactions are redox reactions, and they are characterized by something reacting with oxygen to form one or more oxygen-containing compounds. Often that includes water. So remember, one of the ways we could identify a redox reaction was that oxygen was one of the reactants. So in combustion reactions, oxygen is going to be a reactant. These reactions are exothermic. They give off heat. Why do we light a Bunsen burner? To make things cold? No, we do it to make things hot because it's an exothermic reaction. It gives off heat. When we have compounds containing carbon and hydrogen, those are called hydrocarbons, by the way. That comes up in the lab. Hydrocarbons, because they have hydrogen and carbon in them, hydrocarbons. Or if you have compounds that are just carbon, hydrogen, and oxygen, when those combust, they always form the same two things, which is really nice. Carbon dioxide and water. So CO2 and H2O. Those are the only sorts of combustion reactions that we're going to make you predict products for. The products are always the same, carbon dioxide and water. The ethanol in an alcoholic beverage will combust to form carbon dioxide and water. This is the formula for ethanol. We can see it contains carbon and hydrogen and oxygen. It reacts with oxygen to make carbon dioxide and water. Octane in gasoline combusts. So here's octane. It reacts with oxygen, and it forms carbon dioxide and water. This is a hydrocarbon. It only has carbon and hydrogen. So let's write a balanced equation for the combustion of liquid pentane. We give you the equation because we don't expect you to know the formula for pentane. This is another component of gasoline. Well, we gave you one of the reactants, C5H12. What is its physical state? It's a liquid. They told us that in the problem. If it's combusting, what's the other reactant? Oxygen. At room temperature, what's the physical state of oxygen? It's a gas. So when this reaction occurs, the products are the same as any other combustion reaction of a hydrocarbon. CO2 and water. CO2, and the state of that will be a gas, and H2O. Now, you're not going to lose points over something like the state of water, but let's think about this. Combustion reactions are exothermic. Are the products of this reaction going to be hot or cold? They're going to be hot. When you heat water up, it steams, it evaporates, right? So here, water is going to be in the gas state. And that's, you think about it, when you're burning gas in the Bunsen burner or at home on the stove, do you see puddles of water forming? No, but water is being produced. If you hold a cold object high enough above that you're not going to burn your hands, above a burning flame like that, you'll see condensation on the outside of that. Like a glass of ice water, turn the burner on and hold a glass of ice water over it. You'll see condensation appearing because as the water is released in the gas state from that reaction and it hits the cold surface of the cup, it's going to condense and form liquid. Anyway, so we've got our reactants, we've got our products, now we need to balance this. I just like to start at the beginning with the carbons. Here I've got 5 carbons, and over here I only have 1. So I'll put a 5 there to give myself 5. And then hydrogens, 12 hydrogens. Here the hydrogens are in water, so they have to be in pairs. So we'll have 6 water molecules to get 12 hydrogens. And now we need to take care of the oxygens. So in 5 CO2s, we've got 10 oxygens, and then in 6 water molecules, I have 6. So that gives me 16 water atoms. And so over here, to get 16, I need to multiply by 8. If you're having trouble balancing equations, get help from me or a classmate or one of the tutors. Balancing equations is a big deal. Any questions?